extended Kalman filter. The previous example is pretty good in most cases, but have neglected two important facts. Number one, if you're driving your car, you constantly use the calculation, and each round is about 100 milliseconds. After 100 milliseconds, you're in a different place. You're kind of like 5-6 meters away. You're moving. If you're using to trace the missile, that millisecond could be hundreds of meters away. So the previous model has not considered the motion of yourself. In other words, it does not have the prediction. Second, the Earth is spinning. You're on the Earth spins how much? 360 degrees in one day. And that 100 milliseconds will have a 20 meter difference. You spend 20 meter in this 0.1 second. So you have to consider that. And the actually could be have an error of 70 to 90 meters. Okay, then you need a prediction model. So what is the prediction model? The same as the example I gave last time by data ranking. So by using the extended Kalman filter, we have an advantage of the predicted model. That means I take the advantage of data ranking, include my own speed in last step, include the speed of the Earth is rotating itself, and then the state variable have 8 variables, x, y, z are the positions. And that's the improvement. Vx, vy, vz are the velocity you had. Assume data ranking always assume from one time step to a next time step you have a constant speed, but you do have these 3 speeds along the 3 different directions. You have the bias, that's the same as the least square method, and you add another one, that's the time drift. So why you still need the time drift? Well, among this 100 milliseconds or 70 to 90 milliseconds from the satellite signal to the clock, your clock in this time has a drift, could be less than a nanosecond. But a nanosecond is still a few feet, a few meters away. So you need to include the drift of your clock as another variable. So we now have 8 variables instead of 4. Okay, so what is the relationship? Well, the relationship is easier to write down this way. You know the x now equals x before, just call it x0, plus vx times dt. That's the data ranking. And so is the y now equals the y0 plus y dt. Z now equals z a moment ago, and the vz dt. That's 3 obvious equations. And then you assume the speed does not change, actually change. Then the vx equal itself, and the vy equal in the 2 step. Now this is the time step. K, usually we call it k minus 1. That's what we did all the time, k minus 1. And the v does not change, but you can include the change if you know your acceleration. But the satellites do not know your receiver may do not know your acceleration. unless you have the IMU. Well, next, what you know? Another equation is the B. The B in K equal to B a moment ago plus the dt times the drift of time. So that's another actually times C. You got this prediction model. That's linear, right? That's a linear model, very free. Okay, so you have a linear prediction model, but an non-linear measurement model. You understand that? So the measurement model, to make it easier, is the rho equals the distance from the satellite to the user plus the bias plus the other V is a different V. That's the white noise. That's the white noise. Okay, we already talked about the measurement model, and the whole idea is again minimize this in your camera filter, and then you use the linearized measurement model. This linearized measurement model based on this satellite geometric matrix HK. That's the satellite geometrics. Okay, so we just use the standard camera filter. The only difference is in each step you need to recalculate this HK because it's not the same. Why not the same? The satellite is moving. In each round, they move to a different position, and you are yourself also moving, and then it's not the same. All right, and then you know how it works. The input f is the function I gave, the linear function. Where's the f? No, this is the f. This is the f. So what I write down here. And then g is the distance formula. Q and R are the standard deviation, sigma 1, sigma 2 of the Q is the white noise for the prediction model, and the R is the white noise for the measurement model. And Z is the measurement, come from the measure file, the distance file. X, P, X state, those are the state variable. X state is the state variable. X is the a priori state. And no, actually, the X is the input state from last calculation. And the X is the a priori state. The X state is the posteriori state. You remember the 3 steps, right? The input, then you do a prediction. In another word, the X is the prediction, and the X state is the last state after the update, is the posteriori state. Well, after you have this, you see the function called the extended camera filter. You need to copy the command line and return to this x0, p0. The x0 is the input state for the next stage, but is the output state for current state. P is the covariance. You learned that. And then the rest of them are noise. We always have that. Anyway, you got the idea. You got the input F, G is the measurement, and that's the G. And then you have 4 components because you have 4 satellites. So we started the process, and we discussed that. Z is the current measurement, A is the X is the a priori state estimate, and the X state is the one you're going to return. And the X0, P0 is a posteriori state. Now, what's next? What's last? The last thing is calculation. I have 7 steps. You remember that. Step 1, do the data ranking to your function f. You just use your f. You know the f to do the data ranking. Second, find the Jacobian, the transition matrix. That's easy because it's a linear. That's an easy matrix. The third step is the hardest step. You need to take the partial derivative, and the H is the satellite geometric matrix. We learned the last lesson. Now, this 3 steps finishes the prediction, and then 4 steps for the update phase. Step 1, figure out the covariance based on your a priori state, and you figure out the covariance, and then find the K-mar gain. Look at the difference between the measurement and your prediction. You can figure out the K-mar gain. From the K-mar gain, you update your state variable, and then you update your covariance of your estimate. Then after you finish this, you go back to here and iterative calculation. So I think that's the end of the story, but I wanted to emphasize one more time about what is the whole deal of this K-mar game. Put it here. Look, this is your updated state. This is your predicted state. If the K-mar gain equals 0, that means you neglect the measurement. Doesn't matter. You just use your prediction, data ranking. On the other hand, if this covariance is too big, this K won't be 0. Instead, the K will put the heavy weight on the measurement. Then your measurement will significantly increase, update your position. Why? Because this Z is your measurement, G of XP is your prediction of the measurement. And that deviation will tell you how much you need to lean towards your measurement. So the K-mar filter, the K-mar gain, basically take an optimized weight to give the due trust to what is more reliable. The prediction is more reliable or the measurement more reliable. It really depends. How do you know which one is more reliable? That's why you always figure out this P. That P tells you which one is reliable. If that P is too big, means your prediction is very unreliable. But if this covariance here, this term is big, that means your prediction is bad. Your measurement, this one, you really tell you the measurement is bad because this noise is the measurement noise. That tells you how bad is your measurement. And this one tells you how bad is your prediction. And then put it together, they're going to balance it. Put the best trust to the more trustworthy a little bit, but take both. That's the synergy. Basically, that word you should know is the synergy of the data ranking and the measurement. That's why that's so powerful.